Ever wondered how movies and games make objects look so real under different lights? What if we could take a 3D model and instantly change its lighting, texture, or even material, like turning a wooden table into a shiny metal one? That's the magic of relightable 3D assets, and today we're diving into a breakthrough that's making this possible. The challenge: breaking down a 3D object into its core parts, geometry, its shape, material, how it reflects light and lighting. It's like trying to separate the ingredients of a cake when they're all mixed together. Traditional methods struggle here, especially when dealing with complex surfaces or reflective materials. Enter Gaussian Splatting, a technique that uses tiny glowing clouds, Gaussians, to render 3D scenes quickly. But here's the catch: these Gaussians are discrete like pixels, making it hard to enforce smooth geometry. That's where signed distance fields, SDFs, come in. Think of an SDF as a digital map that tells you how far you are from an object's surface. It's super useful for defining shape, but integrating it into Gaussian splatting. That's where the real innovation happens. The researchers behind this paper didn't just add an SDF, they discretized it. Instead of a continuous map, they encoded SDF values directly into each Gaussian. Imagine each cloud carrying its own minimap of the object's shape. This lets them link the SDF to the Gaussian's opacity, how transparent or solid it looks, enabling super efficient rendering without the slow, energy-heavy ray marching process. But here's the tricky part: discrete data can't easily use gradient-based rules like the iconal loss that keep SDF smooth. So they invented a projection-based consistency loss, a clever way to align the Gaussians with the SDF's zero-level set, the object's surface. It's like using a shadow to check if your 3D model is sitting correctly on a table. The result: higher quality relighting with 80% less memory than previous methods. Their spherical initialization trick also prevents the model from getting stuck in local minima, those pesky dead ends in optimization. Now let's talk about the surface traits that make relighting possible. Think of a surface as having 4 key ingredients: albedo, base color; normal's surface orientation; roughness, texture; and metallicity, reflectiveness. Traditional methods often blur these properties, especially on shiny surfaces like polished metal or glass. This research solves that. They developed a math-driven approach to separate these traits with surgical precision. Imagine a system that doesn't just capture a photo but deciphers a material, SDNA. They tested it on datasets like Glossy Blender and Shiny Blender, where surfaces range from super slick to rough, and compared it to other cutting-edge techniques. The results: pure gold. When they checked how well the method handles relighting, like how a surface looks under different lights, their approach scored a PSNR of 29.31. For context, that's like upgrading from a grainy snapshot to a crystal-clear HD photo. In some cases, it even nailed tiny details, like the faint ridges on a brick wall, outperforming other methods. Here's the magic: their system splits a reflective surface into clean, separate maps. The albedo map shows the base color, the normal map reveals the surface's angles, like the curve of a car's hood, and the roughness map highlights texture. Think of the subtle grain in a wooden table. It's like seeing a car's paint, its curves, and its shine all at once. And when they tested it on real-world scenes, the normals stayed smooth but super detailed, key for making virtual objects feel real. This isn't just about better graphics, it's about tricking our brains into believing digital worlds are real. From virtual reality to blockbuster films, this precision could change how we interact with tech. So next time you see a flawless reflection, remember, it's the result of math, creativity, and a whole lot of pixel-perfect science. Thanks for watching. If you want to see how this works in action or dive deeper into the math, check the links in the description. Stay curious, and we'll see you next time.